All right. So, again, not a huge difference between lenses and mirrors. The ray diagramming is very similar. One thing that lenses do not, we don't care about, that mirrors do have, is a center of curvature. So mirrors have a center of curvature and then a focal point that is half the center of curvature. So you got your center of curvature right there, focal point is half that distance. With lenses, you don't have a center of curvature, but what you do have is a virtual focal point. You have a real focal point and you have a virtual focal point. Or you have a primary focal point and you have a secondary focal point. That's where lenses get a little strange. Okay, so there are two types of lenses. We're not going to worry about flat lenses because a flat lens is a window. So we're not going to worry about flat lenses. We have two types of lenses. We have a concave lens, which is a diverging lens, meaning the real rays will diverge. Now, again, light is wherever, or the real side is wherever the light is. So with a lens, this is the real side, and this is the virtual side. Real, virtual. A concave lens is a diverging lens because the rays diverge. A convex lens is a converging lens because the rays converge. Make sense? Rays move towards the thick part of the light because they bend more where the lens is thickest. So the rays are going to bend more where the rays are thickest, so they're going to bend towards the thick part. The diverging lens has thickest on the outside, they bend out. A converging lens has thickest in the middle, they bend in. Your glasses, by the way, are diverging lenses. You might notice, if you look at your glasses, that they're thickest on the outside and thinnest in the middle. So your glasses are actually concave lenses. Unless you're farsighted. Very few, I don't know if any of you are farsighted. It looks like most of you are nearsighted like me. It also makes contact lenses possible. Contact lenses have to be thicker on the outside and thinner in the middle, so they stick on your eye. You can't wear contact lenses if you're farsighted. By the way, nearsighted means you can see near, but not far. Farsighted means you can see far, but not near. And it gets more complicated after that. Okay, so moving on. I think maybe somewhere in this place. There's my button. Okay, button. Who has the button? Okay, so there's our concave lens. The rays diverge, and diverging lenses do make images. They just make virtual images on the same side as the object. Okay. So concave lenses do make images. They just make virtual images on the same side as the object. So if you were to classify this image, what would you call it? What three words would you use to describe it? Virtual, reduced, and upright. Yeah, virtual, reduced, and upright. Convex lenses are the ones that usually people want to use, even though they're not supposed to use convex lenses. They want to use convex lenses. Convex lenses, the rays go out and they converge. Convex lenses, oops, hey, go back. Come on, it's moving slow again. Try that again. There we go. So if you were to classify this image, you would call this real and inverted and reduced. And again, what kind of image you make depends entirely upon where the object is with respect to the focal point. That's what we're going to do ray diagramming today. Okay. So does this stuff make sense? What we're talking about? All right. Lens equations work just like the mirror equations, except for one small change. Okay. First and foremost, the object is still always real. DO and HO will always be positive. Okay? Objects are always real, so DO and HO will always be positive. The image, if it is virtual, will get a negative DI, and if the height is inverted, if the image is inverted, the HI will also be negative. And the focal distance will be positive or negative depending on where it is. And I'll explain that in a little bit when we do our ray diagramming. It'll make more sense. You notice the only difference between the mirror equations and the lens equations is this term. So the radius of curvature for a mirror, the focal point is 1 over f equals 2 over r. For a mirror, this term is gone. For a lens, this term refers to the index of refraction of the material. In other words, the higher the index of refraction of the material, the closer your focal point will be to the radius of curvature. This is called the lens maker equation. And I say used in lab, but the lab we're actually using, the simulation we're actually using, it went ahead and they made the index of refraction of the material 2 to make it easy. Make it 2, so the term just drops out. So for the simulation, we're not going to worry about it. But this is the lens maker equation. Okay. Beyond that, the math is exactly the same. It's still 1 over f equals 1 over do plus 1 over di. Math is still exactly the same. So beyond the lens maker equation, and again, this term, I've never seen this actually used in exercises. Usually they just make the focal point half the radius of curvature again, assuming the index of refraction is 2. But if the index of refraction was not 2, then you have to use this. Okay, questions? Okay, there's our example. Magnification is once again still the ratio of the height of the image to the height of the object, or the height of the distance of the image to the distance of the object. Negative distance of the image to the distance of the object. Q and P. Why did I use P and Q instead of DI and DO? Because some textbooks still do. I have AP and college level textbooks that still use P and Q instead of DI and DO. So that's why I mentioned it up there. The Q is DI and the P is DO. I hope one of these days the textbooks will be like all agreeing with the College Board. The College Board used to use P and Q until about a decade ago. They're like, why are we using P and Q? Let's use DI and DO. So they use DI and DO. Unfortunately, still a lot of textbooks still use P and Q for reasons no one knows. Okay. Am I being clear? Okay, any questions so far? Right, give me a thumbs up. We're ready to do some ray diagramming practice. All right. Do you have your colored pencils? Do you have your ruler, your backup ruler? All right, so ray diagramming, very, very similar to mirrors. You're still doing parallel focal parallel into the center, only the things change a little bit. Okay, so your first ray through a lens is still parallel focal. But you got 2 focal points. Which focal point do you use? You use the converging focal point. So, for a convex lens, a converging lens, this is focal point number 1. This is focal point number 2. Focal point number 1. Focal point number 2. Primary focal point. Secondary focal point. Focal point. Opposite focal point. Focal point. Bizarro focal point. Good focal point. Other focal point. You, them. Okay. And it switches for a concave lens. For a concave lens, this one's the primary focal point, and this one's a secondary focal point. This one's the primary focal point, and this one's the secondary focal point. foremost, we do not break the rays at the device. We break them at the normal. So let's draw in our normal. I'm going to make my first ray red. Red will be my first ray. So your first ray is still parallel focal. So line up your rays, go parallel to the principal axis. When you strike your normal, then go focal point. Real, virtual. There's ray number 1. Okay, give me a thumbs up if you got ray number 1. Your ray looks like my ray. Maybe a different color. Okay, ray number 2. Ray number 2 also goes focal parallel, but you use the opposite focal point. So you line your straight edge with the opposite focal point, in this case, the virtual focal point over here, and you go focal. When you hit the normal, then parallel. Real parallel, real parallel, virtual parallel. Ray number 2. And once again, this like aiming ray, if you will, the ray that hits the normal will never make an image. It has to hit the normal first before it makes an image. Most of you aren't going to be here tomorrow because you're filling out ACT paperwork, unless they get done in time. Mr. Stuckenberg hopes you'll get done in time so you can come in and do the simulation tomorrow instead of Wednesday. It's a really cool simulation. Image around. Zooms around. Okay, so does that make sense so far? We're using the opposite focal, then parallel. Now it looks like we got an image. Yay! Now here's the cool thing about lenses. Their check ray is always through the center of the lens. That's it. So you line up your object with the center of the lens, like so. It's virtual on this side, and real on this side. So your third ray always goes to the center of the lens. You don't need to measure any kind of radius of curvature or anything. You just go right to the center of the lens.
Oh, I don't understand. We're just gonna draw lines and make it closer and another dash line. It's okay. I know that. It's fine. I'll see what it is.
Wasn't that fun?
I know.
Now let me warn you. Something in your brain is going to turn every lens you see into a convex lens. Be careful. On the tests and quizzes, what I tend to find is people draw the ray diagrams properly for convex lenses. They do the same thing for concave lenses, because convex lenses just make sense to us. So just be advised that things switch when you talk about concave lenses. All right. Give me a thumbs up if you got an image looks kind of like mine. All right, let's describe this. Again, just like with mirrors, we use 3 words to describe our image. What's one word you might use?
Real.
It's real. Yeah, it's on the real side. It's real.
Reduced.
What else?
Reduced.
There's a very good chance it's reduced. We're going to calculate here in a second. And what else?
Inverted.
Inverted. Yeah, it's upside down, so it looks like to be inverted. In determining if it's real or if it's magnified or reduced, we got to do a little math. Now realize this distance here, this is DO. From the image, from the object to the normal is DO. From the normal to the image is DI. And magnification is negative DI over DO. So measure those and see if it actually is in fact reduced. Do you get an M that is less than 1 or larger than 1? Or with a magnification, with an absolute value of less than 1 or an absolute value of more than 1? And again, I'm going to use your numbers, not mine, because your numbers are different than mine, obviously. Yep.
If magnification is more than 1, is it
Magnified.
okay? And then if it's less than 1, it's reduced.
Yep.
Okay, so it's magnified.
Yeah. If your magnification has an absolute value that is larger than 1, it's magnified. If it's less than 1, it's reduced.
So it's, I get magnified then.
Okay.
Wait, what'd you put?
So what did you, give me a DI. What did you get for DI?
I got negative 7.97.
So negative 7.9 centimeters. And DO?
6.6.
6.6. So you got a magnification of 1.2?
Yes. Negative 1.
Negative 1.2, yeah. So again, so the 1.2 tells you it is in fact magnified. And the negative tells you it's inverted. So the negative part of the magnification tells you it's an inverted image, and the 1.2 being larger than 1.0 tells you it is in fact magnified. Yes?
If that was a positive value, would it then be upright?
Yes.
Okay.
Yep. So magnification is negative DI DO. It's also HI over HO. So the HI is negative, and the O is positive. So you're going to get a negative value for the F again, because your HI is down. All right. Did we go too fast, or was this just about right? All right. Okay. Now the next image, the next object is inside the focal point of our convex mirror, convex lens. So let's do our same process. Draw our normal. I'm going to see if I can leave the rays on the page and see what happens for the two convex, and then I'll erase them for the two concave. Okay, for our first ray, mine is red. It's still parallel focal. So parallel to the principal axis, breaking at the focal point, real focal, virtual. Ray number 1.
How do you know which focal point to go to? Because I thought the primary was the one that was on the image side.
The primary focal point is one where the rays converge. So rays converge on this side for a converging lens, this side for a diverging lens. Does that make sense? So for a converging lens, the rays come through and they converge on this side. And they move towards the fat part of the lens. Okay? Make sense? Does that make sense?
Yeah.
Okay. For a diverging lens, the rays come in and they diverge on this side. They diverge on this side, so that means they trace back and converge to this side. Does that make sense? That's going to be the hardest part with diverging lenses.
Converging lens are on the right side. Because
Yes, yes,
converging lens right side, diverging lens is left.
correct. And again, this is what we practice.
So the real side is whatever like side they're technically looking at?
No, the real side is always on the right side of a lens. So the real side is always where the light goes, and light goes through a lens. So regardless of what kind of lens you have, real side is going to be on this side, virtual side is going to be on this side. Good question. Okay, so does this make sense what happened?
Yes.
We went parallel, then focal? Okay, so next ray, opposite focal, then parallel. So we're going to line up our object with the opposite focal point, like that. Okay, so I'm lining up with the opposite focal. I'm going to go to the normal from the opposite focal. Then I'm going to bend it parallel to the principal axis. The real line and the virtual one. Ray number 3.
Wait, so that does not connect to the virtual focal point?
So the second ray, we line up our straight edge from the object to the opposite focal. Opposite focal's over here. We still trace the ray to the normal and then break it at the normal from, so it goes opposite focal and then parallel, parallel.
I'm still confused on how you know like which side is dashed and which side is solid.
Okay, excellent question. If I'm light, I want to go through a lens. So the real is wherever the light is. So I go through a lens, now I'm real. I'm real no matter what. So a lens is a transparent or a translucent object. So light goes through the lens. This is the real side of every lens no matter what. Solid lens.
It's the right side because that's the
That's where the light goes.
But for mirrors it's different.
For mirrors, yeah, because mirror light bounces off a mirror. So the mirror, light comes in and bounces off. This is the real side. This is the virtual side behind
So
mirror.
mirrors, it's always the right side? Or does it depend on
For mirrors, the real side is wherever the object is. For lenses, the real side is the opposite side of the object. Okay. If you're still struggling by the end of today, don't worry, the simulation will help quite a bit tomorrow or Wednesday. Okay, so if you have two rays that look kind of like my rays, give me a thumbs up. Okay. If you're struggling, put your hand up and wave it around. All right. So it looks like we got an image right there. Pretty cool. So let's draw our check ray. And again, the cool thing about lenses is the check ray right through the middle of the lens. So line up our object with the middle of the lens. And there we go. It is going to be virtual on this side and real on this side. Ray number 3. So I lined up my straight edge from the top of my object to the center of the mirror, or sorry, the center of the lens. I made a virtual line on the virtual side of the lens, a real line on the real side of the lens. I made an object. I made an image. Ooh.
There's my image.
Fake. It's not. It's virtual. Please don't use the word fake. That will not earn you any points on the AP test. I promise you. Optics is one of those things that on the AP2 test, you really hope it has a big point question. because optics is super easy on the AP test. Laughably easy. I'm not exaggerating. It's laughably easy.
I don't know.
There are some. So the AP Physics 1 test is pretty tough because the concepts are simple. The concepts in optics and thermodynamics and electromagnetism are a lot more complex, so the questions tend to be easier. And every optics question I've seen on the AP Physics 2 test has been like, you can handle it on the second day of optics. Like once you ray diagram, done. Ray diagram equation, yeah, done. Okay. So let's go ahead and use 3 words to describe this. What's one word we might use?
Virtual.
Yeah, it's virtual. It is virtual. It's hanging out on the virtual side. What else?
Up magnified.
It's magnified.
And that's it.
And it's upright. It's upright and magnified.
How do you tell it's upright?
Okay.